provenance. I'm Dr. Kaya Fenn, and I'll be the chair and moderator of this session. Before we start, just a little bit on housekeeping and the format. First, we've all been through variety and large number of Zoom meetings, but please make sure that you are muted unless you really intend to speak, so we can have uninterrupted audio of our keynote speaker today. So the talk will be about half an hour, 40 minutes. And following that, we'll open the floor to questions from the audience. Whether you have signed up via our link or are you just joining last minute, that's absolutely fine. Feel free to ask the questions either throughout the session or at the end. We'll finish the session with a presentation from one of our ERC members presenting their own data and asking for feedback from the community. So please stay on until the end if you can. Like I said, you are able to ask questions throughout the session. Please use chat. I do understand that the 223 participants may be somewhat frightening to our especially early career members of the workshop. So if you feel a little bit frightened by it, feel free to drop a question just directly to me if you don't want everybody to see the question, and I'll then ask them anonymously at the end. If there are several themes, I'll pull them together and ask them at the end, but more sort of thematically. You are also able to ask questions yourself at the end by raising your hand, and I'll invite you to ask questions and unmute yourself at the end. So for our speaker today, I don't think Peter really needs an introduction, but I'll give it a try to be very brief. So Peter is a professor of geochronology at University College London and has been a really important contributor to the field for almost 2 decades, I think now. And a lot of his interests center around geochemistry and geochronology. And in his work, he uses variety of isotopic systems, but just to name a few: uranium, lead, and argon, uranium, thorium, helium. But what's important for us as a Loess community, he often applies those tools as a sediment provenance tools and to trace the sources of sediment, especially in the Aeolian context. And he worked extensively on provenance of sediments in Asia and Africa. But he has also led the way in statistical research and software development in the field of geochronology. And I think most of us here are very familiar with either isoplotter or density plotter or provenance package, which Peter has worked on developing. So it is my great pleasure to hand over to our speaker today. Peter, over to you.
Thank you very much, Kaya. Let me share my screen. So I hope you can all see this. So it's great pleasure and honor to be talking to so many early career scientists today. So I really enjoyed yesterday's workshop by my friend and former classmate Jan-Pieter Beulaert, and I hope that you will learn as much from my presentation as I have learned from his. So I'll be talking about some statistical approaches to making geological sense of large data sets in sedimentary provenance analysis, which, as I'm sure you all know, but doesn't hurt to remind you of, is the science and art of figuring out where sediment, siliciclastic sediment, came from. So this could be either fluvial sediment or windblown sediment, Loess, which you are all interested in. And over the years, a variety of different provenance traces have been proposed and tested, including the bulk chemical composition of sediment, the mineralogy of sediment, or the isotopic signature contained in some accessory mineral phases. And I will be giving examples and talking about all of these different provenance proxies in this workshop. So in some cases, even a single grain of sediment, of sand or of silt can already tell you a lot about its provenance. For example, it suffices that you find a single grain of diamond to confirm the presence of kimberlithic lithologies in the hinterland. But of course, in most cases, one grain is not enough, and you need to analyze multiple grains per sample to really characterize that sample and extract a characteristic fingerprint from it. And immediately when you start working with multiple numbers, you run into statistical issues. And I will very briefly, at the beginning of my presentation, give you an example of one statistical issue involving multiple single grain ages of geochronology and a statistical solution to that visualization problem. Most studies nowadays involve, of course, not one, but multiple grains of or samples of sediment. And then really statistical help is almost indispensable. And I will introduce multidimensional scaling as a simple yet effective tool to make sense of multi-sample data sets in a provenance context. And then over the past few years, and increasingly in the future, it has become and will become more common for sedimentary geologists to combine multiple proxies and apply them to the same samples. For example, a study could combine distributional data, so for example, uranium-lead, zircon-uranium-lead geochronology, with the bulk composition in terms of major and trace elements on the same samples, as well as the petrography and the heavy mineral composition of those same sediments. So these are count data, as well as recently there's an increase popularity of varietal data in which the chemical composition of individual grains is used to extract a rich form of fingerprinting data. So all these different approaches to characterizing sediment can be applied to the same sediments, producing very rich, very big data sets. And analyzing those data sets is virtually impossible without the help of statistics. And in my presentation, I will introduce two avenues to making sense of such big data. One is called procrustes analysis, the other is called three-way multidimensional scaling. Before I do that, however, I would like to first walk you through the application of distributional, compositional, and count data to multiple samples. So I will first discuss these three different data types before then bringing them together. The fourth data type, varietal data, I will not discuss today because I don't have the time to do so. But if you have questions about this particular type of data, I'll be happy to expand on this during the questions at the end of the session. All right. So let's get started with distributional data. So detrital geochronology, for example. The name distributional data refers to the fact that we are using the distribution of numbers extracted from grains of sediment as a fingerprinting tool. So distributional data, such as zircon, uranium, lead, age distributions, can be stored on a computer as lists of numbers, where each list corresponds to a sample and contains a variable number of numbers, which in this case represents the ages of individual grains of zircon in millions of years. Now, simply visualizing the raw data in a tabular format as shown on the slide is obviously not the best way to bring out the information content of these data sets. So we need a graphical way to show the data. And in the early days of detrital geochronology, until about 10 years ago, that graphical device was the probability density plot, which was implemented in popular software such as isoplot, and is constructed as follows. First, you take your single grain ages in millions of years, and you rank them from young to old. In this case, there are 4 ages, but of course, in real data sets, there will be 100 or more. And then on top of each of these ages, we stack a bell curve, the width of which, pardon, the width of which corresponds to the uncertainty of the single grain measurements. If we then take the sum of all these bell curves, we get this continuous line, which is a probability density plot. Now, as I said, the PDP was a very popular graphical device. It was used in thousands, if not tens of thousands of studies. But unfortunately, it's wrong. It's easy to see that it is wrong in the end member case where the analytical uncertainty of the measurements is very small. If you put a lot of effort and a lot of money into your detrital geochronology and you analyze every grain by TIMS, for example, which is a very precise technique, then your measurement uncertainties are very, very small, perhaps a per mil or something. And the PDP turns into a number of spikes, which really do not serve any useful purpose, don't look like a probability distribution, are no longer a continuous curve. There are other problems with the PDP as well. I don't have time to go into the details of them, but you can read about them in this paper. This paper proposes a standard statistical visualization technique called kernel density estimation as a better alternative to the probability density plot. So a KDE is constructed in a very similar way to the PDP. We rank the ages from young to old. We stack a symmetric curve on top of each of the measurements. The crucial difference is that the width of these curves is not related to the analytical uncertainty of the measurements. It's calculated using independent means, but it still produces a continuous curve. So nowadays, KDEs have overtaken PDPs as the most popular tool for visualizing the detrital zircon age distributions, and I will use KDEs in my presentation today. For example, in this data set here, which comprises 13 samples from the Chinese Loess Plateau, the Yellow River, and its Tibetan headwaters. Each of these 13 samples have been analyzed by the detrital zircon uranium EDS geochronology. 152 grains in sample 1, 117 grains in sample 2. So there are differences in sample size, but that's not a problem because you can plot them all as kernel density estimates on a similar scale from 0 to 3 billion years. Now, if you squint your eyes and you look at these wiggle plots from a distance, you may be able to see some similarities and differences between them, and you may be able to extract some provenance information from them. But I think you'll agree with me that that would be a very subjective exercise, and it would be useful to be able to do this comparison a bit more objectively. The problem is that when you've got 13 samples, there are 13 times 12 divided by 2 is 78 pairwise comparisons. That is too many for the human brain to process. So I'll introduce multidimensional scaling as I think that multidimensional scaling, like the proposer, that is a very useful technique to simplify the interpretation of these data sets. So multidimensional scaling sounds like something very complicated, but it is really very simple. It has existed for 90 years now. It's a standard statistical technique that is most easily illustrated using not a geological example, but a geographical example. So here is a table of pairwise distances between American airports. So the distance between Atlanta and Chicago is 587 miles. The distance from Denver to Los Angeles is 831 miles. So this is a table with positive numbers that is symmetric around a zero diagonal. Those are the requirements for multidimensional scaling. So given a table of this form, if you plug it into this black box, it's basically in its simplest form just a sequence of matrix manipulations. This table can be turned into a map of the United States, in which we can see New York City in the northeast, Miami in the southeast, Seattle in the northwest, and San Francisco in the southwest. So it seems like the multidimensional scaling has faithfully reproduced the map of the United States. Now, if you want, you can measure the distance between these cities in centimeters or inches on this screen or on a piece of paper. And you can plot these fitted distances on the MDS map against the input distances in miles from my input table. That is called a shepherd plot. It allows you to visually assess the quality of the MDS fit. Now, in this case, that quality is very good. We can see that MDS has very successfully managed to visualize this table of pairwise distances as a map. The fit is very good, but it's not perfect. If you look at these circles here, they are not exactly on the line. And this simply reflects the curvature of our planet. It is impossible to put a shell, an arrangement of points on a shell, and project it onto a flat surface. So that's where a little bit of dispersion here originates from. Now, how can we apply multidimensional scaling to the tritozircon uranium lead data? Well, first of all, we will need to somehow extract distances between these age distributions. Those distances will, of course, not be expressed in miles. They will be statistical distances. And there are several ways to quantify the dissimilarity between probability distributions. I won't discuss all of them, but the simplest, and I think still the best way to do so, is called the Kolmogorov-Smirnov statistic. Russian names, sounds complicated, but is again very simple. What you do to calculate the Kolmogorov-Smirnov distance is you rank the ages from young to old. In this case, there are like 100 grain ages, and you rank them, and you plot the cumulative percentage of the grains of the ages against the age. So for example, here, sample Y, which is a Yellow River sample, about 60% of the grains in this sample are younger than 500 million years, and about 50% of the grains in sample 5, which is a sand dune, are less than 900 million years old. All right, so you can obtain these cumulative distributions. The KS distance is the maximum vertical distance between these two curves. It is a number between 0, which corresponds to a perfect overlap between the two curves, and 1. If the Kolmogorov-Smirnov distance is 1, it means that there is no overlap. So intuitively, it does really fit the definition of a distance. So what we can do is we can combine, or we can compare each pair of samples of zircon, uranium, lead age distributions and calculate the Kolmogorov-Smirnov distance between them. And that's shown on this table. I have multiplied all these distances with 100 to get rid of the decimal places. So here are the not American airports, but sample locations. And these are the distances. The smallest number on this table is 7, indicating that sample Y, the Yellow River, is very similar in uranium lead age distribution to T, which is a compilation of bedrock samples and sedimentary rock samples in the Tibetan headwaters of the Yellow River. So let's check this. So sample Y has 2 peaks in the Phanerozoic at 250 and 500 million years, and it's got very little going on with the Precambrian. It is very similar indeed to sample T, which also has these 2 peaks and very little going on with the Precambrian. Note that there's a very different sample size between these two. The Kolmogorov-Smirnov doesn't really care about that. So T and Y are very similar. The table implies that 63 is the biggest number, so L, which is Chinese Loess, and sand dune number 8 should be very dissimilar. So let's try that. This is sample 8, has 1 peak in the Phanerozoic, 2 peaks in the Precambrian. L has again 2 peaks in the Phanerozoic and very little in the Precambrian. They are very different. So it seems like this simple Kolmogorov-Smirnov statistic has effectively captured the key differences between the different age distributions in my data set. These Kolmogorov-Smirnov distances, again, are positive numbers. The distances are symmetric around the zero diagonal. They fulfill all the requirements for multidimensional scaling. So we can plug this matrix into this black box and it spits out a map not of the United States, but of sediment samples. And the distances we can then calculate, we can measure the distances just like for the American airports between these different points on the map. And it visually already confirms what we saw before. The smallest fitted distance is that between the Yellow River and the Tibetan headwaters. So these 2 points plot close together. These 2 points plot close together, whereas samples 8 and L plot far apart. So visually, it seems to have done the job at capturing the key differences quantified by the Kolmogorov-Smirnov statistic. So we can plot these measured distances against the input distances from this table and produce a shepherd plot. And the scatter of this of the data points around the shepherd plot can be quantified with a number called the stress. And you can then look up this stress value in a table to see whether your fit is perfect, excellent, good, fair, or poor. In this case, the fit is good. So we can kind of start making geological interpretations from the MDS configuration, having this confirmation that the MDS map has faithfully captured the Kolmogorov-Smirnov distances of the input data. So let's do a bit of geological interpretation. Here again is my multidimensional scaling configuration, which each point corresponding to a location on in the field area. Samples that plot on the right-hand side of the MDS map all correspond to samples from the southwestern part of the Loess Plateau and the Yellow River. Samples that plot on the left-hand side of the MDS configuration all come from the north eastern part of the Loess Plateau, indicating that these samples have a different provenance than those samples. And this is remarkable, this clustering, because nowhere in my analysis did I specify the latitude and longitude of the samples. This grouping really came out of the uranium-lead age distributions. This is still a subjective interpretation, but it is a lot less subjective than just visually assessing the shape of the kernel density estimates. Okay, so that was distributional data. Let's now move on to the second type of provenance proxies, which are compositional data. So we've got the bulk composition in terms of major and trace element composition of sand or loess can also be used as a provenance proxy. And unlike distributional data, which are best stored on a computer as lists of lists, compositional data can be visualized as tables. Tables that contain positive numbers and have both row names corresponding to sample numbers, in this case samples from the Namib Sand Sea in Namibia and the Orange River on the border between Namibia and South Africa. So row names are samples, column names are in this case major oxides, silicon, aluminium, etc. So these tables can be analyzed or have traditionally been analyzed. Well, let me just say, yeah, so tables like this also contain a lot of numbers, cannot easily be interpreted by tabulating them. We again need some kind of statistical help to make geological sense of such tabular data. And in statistics, very often these kinds of tables are subjected to a statistical technique that is closely related to multidimensional scaling. I'll explain why that is later on. A statistical technique called principal component analysis. So I will illustrate, I won't go into the mathematical details of principal component analysis yet, but I will just illustrate the principles behind it or the application of it using not a geographical context, but a context of crime statistics. So here is a table, looks very similar to the table of compositional data that I showed in the previous slide, but instead of having sample locations, we've got American states, Alabama, Alaska, Arizona, all the way to Wyoming, so 50 states. And we've got 4 columns tabulating the number of murders, assaults, and rapes per 100,000 people per year, as well as the percentage of the population that lives in cities. So this is a table, just like my compositional data, that can be subjected to principal component analysis. It's a technique that is similar to multidimensional scaling, and it will produce a map with all the American states grouped according to similarity and dissimilarity. So you can see, for example, that West Virginia and Vermont are very similar in terms of these 4 statistics, whereas California is very different from Vermont. Now, this multidimensional scaling map has been augmented with labels and arrows corresponding to the different columns. This is called a biplot. It shows 2 types of information. So we can then see what is causing these differences and similarities between states. We can see that states that plot on the left-hand side of the principal component biplot are states with a lot of crime, murder, assault, and rape, such as Alaska and Maryland. States that plot on the right-hand side, like Iowa and New Hampshire, have less crime, less murder, assault, and rape. The fact that all these arrows point in the same direction means that these crimes are all correlated with each other. If there is a lot of murder in your state, there will also be a lot of rape. The second dimension, at a right angle to the crimes, is the percentage of the population that lives in urban areas. So California, for example, has a large proportion of its cities, of its people living in cities. West Virginia and Vermont are very rural states. The fact that this urban population arrow plots at an approximately right angle to the crime arrows indicates that the percentage of the population that lives in cities is independent of crime statistics. So it doesn't matter whether you live in a state with that is very rural or very urban. That in its sense does not have a direct correlation, in itself does not have a direct correlation with crime statistics. Okay, so it would be nice if we could apply principal component analysis to compositional data and interpret our provenance data in the same way as I have done with these crime statistics. Now, unfortunately, we can't directly plug our compositional data into principal component analysis because there's a crucial difference between the data that are normally subjected to principal component analysis and the tables of compositional data that we work with in geology. The difference is that the numbers that we work with here are not only positive, but they add up to a constant sum. The sum of all the major oxides in a rock must be 100%, and that is causing some statistical issues which prevent us from reliably applying principal component analysis out of the box. To illustrate these statistical issues with the analysis of compositional data, I will first discuss a simpler case in which we don't have 11 columns as I do in this data set, but just 3. So let's consider a simple compositional data set with 3 components, X, Y, and Z, that add up to 100%. So each of these black dots represents a sample in a ternary system, and as geologists, we're all familiar with ternary systems. You can plot them on a triangle diagram or a ternary diagram. To illustrate the difficulty and the dangers of applying standard statistical techniques such as principal component analysis to compositional data, let me just take the average of these data points. So I take the averages of the X's, the Y's, and the Z's. I renormalize them to unity, And that produces an arithmetic mean, which is visualized here as a white square. You can see that the arithmetic mean plots outside my data cloud into a meaningless position. So a very basic statistical operation, averaging, cannot be reliably applied to compositional data. Similarly, if you've got very dispersed data, a second summary statistic that is very often calculated in the sciences is the standard deviation of the data. So here I've got three populations: circles, crosses, and triangles. I can calculate the mean of these compositions. I can calculate the standard deviation. I can multiply the standard deviation with 2, and I can use that to obtain 2 sigma confidence polygons for my 3 populations. You still occasionally see such polygon plots in sedimentary geology. You can see on this example why this is a bad thing to do, because in this very extreme dispersed case, my confidence, my 95% confidence polygons plot outside my triangle into physically impossible negative data space. So I hope that these 2 examples show that you have to be very careful when analyzing compositional data using standard statistical techniques like averaging, standard deviations, linear regression, or principal component analysis. These problems had long been known to mathematical geologists, but it wasn't until the 1980s that a solution to this compositional data conundrum was found by Scottish statistician John Aitchison in an influential paper and book, in which Aitchison shows that all these issues associated with the analysis of compositional data can be solved by simply mapping the data from our compositional data space, for example, from our ternary diagram, to a lower dimensional log ratio space. So instead of plotting our data as in a triangle, we map the data to a bivariate space where we take the log of y over z versus the log of x over z, for example. And then Aitchison shows that we can confidently apply standard statistical techniques like averaging, the calculation of confidence regions, regression, etc. in this compositional log ratio space, before then mapping the results back to the ternary diagram where our confidence polygons should stay inside the triangle and everything should be well behaved. This log ratio transformation makes intuitive sense because even though we've got 3 variables here, x, y, and z, the very fact that I can visualize the data on a 2-dimensional computer screen really tells me that there are only 2 dimensions worth of information in this data set. And this bivariate log ratio space much more reliably captures the information content of that 2-dimensional data set than the ternary diagram does. So to wrap this up, if we convert these ternary data, these black dots, to a log ratio space, we calculate the arithmetic mean in that log ratio space and then map the results back to the ternary diagram. We get not an arithmetic mean, but a geometric mean, which plots nicely inside my data cloud, a much better result than the arithmetic mean. Now, log ratio space is also where we need to work if we want to apply principal component analysis to compositional data, or multidimensional scaling for that matter. So multidimensional scaling, as I said in the distributional part of my presentation, requires that we measure the distance between samples. In the case of distributions, that was the Kolmogorov-Smirnov distance. In the case of compositions, bulk chemistry, trace chemistry, the distances can be measured in log ratio space. Each of these points would be 1 sample in multivariate data space. We can calculate the distances between them in log ratio space. These distances are now referred to as Aitchison distances, in honor of John Aitchison, their inventor. So using these log ratio distances, we can populate a matrix of pairwise distances between samples and compositions. And we can subject that to a multidimensional scaling, allowing us to see similarities between samples in 4 and in 5, and differences between samples in 4 and in 8, for example. So this is multidimensional scaling. If we subject that same log ratio transform data set to principal component analysis, we see that the results are identical. Principal component analysis is a special case of multidimensional scaling. Now, principal component analysis has the additional advantage of being able to visualize its results as a biplot. So generally, we don't just use multidimensional scaling, we use the special case of principal component analysis applied to the log ratio data. And that allows us to see that, for example, sodium and potassium contents are enriched in samples in 4 and in 5, are depleted in sample in 3. Sodium and potassium are correlated with each other. Titanium and phosphorus are anti-correlated, and titanium and potassium, or variations in the magnesium-potassium ratio, are independent. What's important point to realize is that, again, PCA is a special case of MDS. Good, all right, moving on from compositional data to our third and final data type, counting data. For example, the petrography or the heavy mineral content of sand or silt, again, using my Namibian sample as an example. I've got, again, a table with 16 samples of sand from the desert and from the river, and 6 different classes of quartz, feldspar, and lithic fragments. These tables look very similar to the compositional data tables, and in fact, people have been treating them as compositional data for many years, but I think this is not entirely correct because there are 2 crucial differences between these point counting data and compositional data. The first difference is that whereas compositional data always add up to 100%, counting data do not. A different number of grains might be counted for each sample, and even though you can normalize all these numbers to 0, the raw data really do not add up to a constant sum. Secondly, point counting data can include 0 values. Unlike compositional data, every sample has at least a few atoms of every element of the periodic table. Counting data can have 0 values because we are working with relatively small numbers of grains measured by a human sat at a microscope. When you put these 0 values into Acheson's log ratio transformation, it blows and it doesn't work anymore. So we can't calculate Acheson distances. Now you can hack your way around this issue by replacing the 0 values with small numbers. For example, 1/2 has often been used, but that's just a hack. It's not a very elegant problem, and it doesn't really work when you've got a lot of zeros in your table. The second problem is this, the fact that we've got a limited number of grains which are causing uncertainties. So here's a synthetic example of 20 samples, random numbers generated from a ternary composition, A, B, C, whose true composition is represented by this black square. If I take 20 samples at random from this population, because I only have, 60 grains per sample, there's a lot of scatter in the results. This scatter is not accounted for by principal component analysis or conventional compositional data analysis. We need a different way to handle those kinds of that kind of sampling scatter. So instead of calculating Acheson distances, both of these issues are addressed by using a different distance metric, the chi-square distance, which is defined by this beautiful column, this beautiful equation. The details don't matter. What does matter is that this equation is immune to 0 values. It suffices that you've got a single non-zero value on each row and each column of your table for this distance metric to work. If you use this the chi-square distance to populate a matrix of pairwise distances between samples, you can then again feed that matrix into an MDS algorithm that produces a configuration which allows you again to see similarities and differences between samples. In this case, using a chi-square distance, it turns out that MDS is equivalent to correspondence analysis, which is a technique that looks very much like principal component analysis, can also be visualized as a biplot showing that sedimentary and metamorphic lithics are correlated. Quartz is uncorrelated with these lithic fragments, and sample N1 is rich in volcanic lithics, whereas N10 is rich in quartz, etc. So again, just like principal component analysis, correspondence analysis is a special case of multidimensional scaling, which allows us to visualize the data as a biplot. So in summary, I've introduced you to three different data types. The trittle geochronology produces distributional data that can be analyzed by multidimensional scaling, vanilla-flavored multidimensional scaling. The major and trace element composition of sediments corresponds to compositional data, which need to be subjected to log ratio transformation using the Aitchison distance. Multidimensional scaling turns into principal component analysis. And finally, petrography heavy minerals are counting data measured at the microscope, and they can be analyzed again by multidimensional scaling using the chi-square distance, in which case multidimensional scaling becomes correspondence analysis. Okay, so we've got three different classes of data that I've introduced to you. All can be summarized on multidimensional scaling plots, allowing us to make sense of data sets comprising multiple samples for any given provenance proxy. But as I said during my introduction, it is becoming increasingly popular to apply not just one, but multiple provenance proxies to sediment samples, because that really tremendously increases the power of sedimentary provenance analysis. For example, the trittle zircon uranium lead geochronology is very popular, but zircon is only 1 part per 10,000 of your sediments. Zircon uranium lead geochronology is blind to lithologies that are very poor in zircon. So by just looking at zircon, you miss a lot of potentially important information. And so it is very useful to augment zircon uranium lead studies with heavy minerals and petrography, so counting data, as well as the bulk composition, major and trace elements of the same samples. So my 16 samples from Namibia and South Africa have been subjected to 5 different provenance proxies here. And you can visualize those as kernel density estimates and as pie charts, but I think you'll agree that it is just impossible to visualize I think there are 17,000 numbers in this data set. This is really a big data set. It's impossible to see patterns or trends in this data set without some statistic or serious statistical help. So I'll introduce you to 2 techniques that can help us make sense of these data sets. At the first glance, or at the first approach, we can start interpreting these data sets by subjecting each of the provenance proxies to multidimensional scaling. So I've got my uranium lead data here, heavy minerals and petrography, the counting data analyzed using the chi-square distance, and my major and trace elements using the Aitchison distance. So I've got 5 different MDS maps, which already are easier to interpret than my raw data, but they're still not easy to interpret. There are some similarities between these MDS maps. For example, N5 and N4 tend to plot relatively close together, and samples T8 and N4 tend to be far apart. But there are also differences between the different MDS maps. They're also oriented in different rotations. MDS configurations are independent of rotation invariant. Some of them are flipped relative to the other. Sample N14 here, for example, it's plotting in a strange place for the bulk petrography. It's not easy to get kind of a consensus view from our data set by just looking at these 5 MDS plots. It's a similar problem to comparing multiple kernel density estimates. The brain is not really well suited to make all these multiple comparisons. A first way to simplify the interpretation of multiple MDS plots is called Procrustes analysis. It's a technique that is named after Procrustes, a mythological innkeeper in Greek mythology, who was a bandit. Anybody who visited his hotel would be tied to an iron bed, would be stretched, or their limbs would be cut off, regardless of whether they were short or tall, whether they were fat or thin. Procrustes managed to fit them all to the same bed, after which he would kill and steal their money. So Procrustes was killed by Theseus, who subjected this bandit to his own treatment. And similarly, Procrustes analysis is a statistical technique that takes multidimensional scaling configurations and tortures them. It rotates them, it flips them, it stretches them, it shrinks them in order to fit a consensus configuration, which in the case of my Namibian data set reveals that samples along the coast of the Namib Sand Sea, including samples 1 and 12, all plot close together with samples of the Orange River, indicating that sand comes from the Orange River and then populates the coastal parts of the Namib Sand Sea, whereas samples N8, N9, N4, N5, they all come from the edges on the eastern side of the Namib Sand Sea, suggesting additional supply of sediment from the West African escarpment that rises steeply towards the east of the Sand Sea. So one diagram to summarize a very big data set is a big step forward in making geological sense of big data, I think. A second way to visualize and interpret large volumes of multidimensional, multi-sample, multi-method data is called three-way multidimensional scaling. As the name suggests, it's a generalization of regular multidimensional scaling that is best illustrated not using a geographical or a crime example, but a psychological example. So in the 1960s, a psychologist called Helm carried out some experiments into color vision. Now, I am colorblind. I can't tell you what I was told. There's a number on this plot. I don't know what this number is. I can't see it. And it's a problem that many people face. Helm was studying this problem by giving 16 different people 9 different colors to 10 different colors to compare. So he was asking to quantify the similarities, the perceived similarities or dissimilarities between the different colors. So what he did essentially was give color strips to these people in triplets, and he asked them to arrange them in a triangular fashion and to put colors that they thought looked similar close together, some colors that were dissimilar, put them far apart, and then he could measure the distances between these colors and populate these dissimilarity matrices, which are symmetric around the zero diagonal. Only the lower half of the symmetric matrices are shown here. But in any case, there are 16 9x9 tables of pairwise distances between green and yellow, blue and purple, etc. We can subject each of these 16 matrices to multidimensional scaling, producing 16 different MDS maps. And that again gives us this multi-plot comparison problem, which can be solved either by Procrustes analysis or by three-way multidimensional scaling, which involves stacking these 16 matrices, these 16 tables, into a single 16 by 9 by 9 tensor, a three-dimensional table of numbers, which can be fed into a generalized version of the multidimensional scaling algorithm called three-way multidimensional scaling, or INSCAL, individual differences scaling. Three-way MDS produces not just one piece of output, but two pieces of output. On the left-hand side are shown the colors. This is like a Procrustes map of the 16 different MDS configurations that would be obtained by these, by subjecting the 16 matrices to Procrustes analysis. This is a group configuration, shows that green and red are dissimilar colors, yellow and purple are dissimilar, green and blue are similar, etc. This is the color circle that you're probably all familiar with. Three-way multidimensional scaling is by far and away the easiest way to obtain the color circle. On the right-hand side are shown not the colors, but the people. It shows on the X and the Y axis the weight that each of these people give to the horizontal axis and the vertical axis of the group configuration. In conventional two-way multidimensional scaling, the X and the Y axis don't mean anything. You can rotate the group configuration, or you can flip it around. The direction doesn't really mean anything. In three-way multidimensional scaling, they are meaningful because they show that people who plot in the lower left corner here attach a weight of 1.2 to the y-axis and a weight of 0.85 to the x-axis. So in these people's perception, they will stretch the color circle, or the color, it's actually slightly elliptical. They will turn it into a real color circle. Whereas people who plot in the lower right corner here, they attach a much stronger weight to the horizontal axis. So they see more than average, a greater difference between yellow and purple, and they attach a weight of only 0.7 to red and green axis. So these people are less sensitive to red-green differences and more sensitive to yellow-purple differences than the average person. So to just make that explicit, by combining this set of weights for the different people in the experiment with the group configuration of the columns, we can obtain 16 different individual spaces. So people who plot in the lower right corner here, in their perception, the color circle is not a circle, but a tangerine. They are red-green colorblind. They're actually more sensitive to differences between yellow and purple. So I belong in this corner here. I am not colorblind. I just see colors differently than people who are plotting over here, who really do see the color circle as a circle. All right. We can apply exactly the same idea to provenance data. Instead of people, we have sample locations. Instead of colors, instead of colors, we have different sample locations. Instead of people, we have different provenance proxies. The people are plotted in the colors, so the samples are plotted as a group configuration, and that looks very similar to the output of the Procrustes analysis. Just like the Procrustes configuration, also the group configuration of my samples shows that coastal samples are similar to each other and to the Orange River, whereas samples N4, N5, N9, N8, and N10, the inland samples here plot elsewhere in the group configuration, suggesting additional supply of sediment from the escarpment, so not from the Orange River. And then instead of people, we've got provenance proxies. There's 5 of them. I've got the trito, zircon, uranium, lead dating, my heavy minerals and petrography, so the counting data over here, and the major and trace elements plot in the lower right corner. So like for the color example, these two sets of weights allow us to attach geological meaning to the axes of the group configuration. My interpretation is that zircon, uranium, lead dating, heavy minerals, and bulk petrography, they are less sensitive to winnowing effects, to hydraulic sorting, than the major and trace element compositions. So major and trace element composition, if you go on a sand dune, you will find placer deposits and anti-placer deposits, dark patches and light patches, caused by enrichment of heavy minerals, which may be very rich in iron, may be rich in accessory minerals, such as monazite, that can increase the rare earth composition of the sediment. Winnowing effects, hydraulic sorting, can strongly affect the major and trace element compositions because they are applied to the bulk chemical composition of the sediment without any mineral separation. In contrast, uranium, lead, heavy minerals, and petrography have been applied to mineral separation. So the effect of hydraulic sorting has been largely undone in zircon, uranium, lead geochronology. So these proxies are less sensitive to hydraulic sorting and therefore more sensitive, relatively speaking, to sedimentary provenance. So my interpretation is that sample N5 and N14 really do have a different sedimentary provenance. Samples N7 and N8 may have similar provenance, but they have been pulled apart by hydraulic sorting effects. All the techniques that I have introduced to you in this short workshop have been implemented in a free software package called Provenance that is programmed in the R programming language. You can access this package from my website. It can be used from the command line. If you know a little bit of R programming, you can access, you can write your own scripts and produce plots like these and apply multi-dimension scaling, etc. to your data that way. If you're not so familiar with the R programming language, there is also a user-friendly query-based user interface that can help you get started with these techniques, which I hope you will find useful for your own research. So with that, I would like to end, and I'll be very happy to answer any questions that you might have. Thank you.
Thank you very much, Pieter. That was fantastic. I think we all agree, and a real insight into what a lot of the time seems to be the black box of statistics that we may apply without knowing what exactly happens within a code or software itself. So that was very, very informative. Thank you.
But there you really, whoop, there's some echo.
Sorry, I completely lost you. I don't know if everybody else, so if you wouldn't mind starting from the top, as in not the presentation, but what you were saying just now.
Yeah, no, I would just, maybe you want to turn off your microphone, because I think there's echo. All right, so I was just saying that what I like about multi-dimension scaling is that even it's a black box, it's not a very dark black box. It's the insides are somewhat still understandable, and especially in the case of in the case of principal component analysis, it really shows everything. It's pretty close to your raw data. It's not completely disconnected from your raw data, like, for example, machine learning can be. Neural networks can be very useful, but there you really don't know what's going on inside. Multidimensional scaling is a traditional statistical technique. It's nothing fancy. It's something you can program from scratch. So it's a black box, but not as black as some other tools that some people might be considering using.
Fantastic. So there is a question in the chat, and please keep questions coming as well. Let's start with the question in the chat. So, hi, Dr. Vermeesch. A very impressive talk. I'm interested in MDS analysis. Do you know other softwares for MDS analysis beside our project?
Yes. Well, so there are two that I could mention. I've got a MATLAB script in my paper on multidimensional scaling, which was published in 2013. There's a link to a website where you could see a MATLAB script. Any programming language, Python, for example, will have multidimensional scaling in one of its packages. It's such a common technique. But it's also part of, in the case of detrital geochronology, if that's your provenance proxy of choice, maybe I should just show you a little demo. I've got another computer program, an R package, in fact, called isoplotter that some of you may have used. It does have a number of tools for detrital geochronology. So you can plot your data as kernel density estimates. There's various options that you can explore here. You can plot your data on logarithmic scales. You can add rug plots, etc. It also has multidimensional scaling in it. So I think that's an even easier way to quantify or to apply multidimensional scaling to detrital geochronology. This tool will only deal with geochronological data. It doesn't do any heavy minerals or bulk chemistry. For that, you will need to use the provenance package or any other similar tool like this. Detrital Pi is a package written by some American colleagues in Python that carries out the same calculation. So yeah, there are lots of options.
Fantastic. I've got Chiara, if you want to come in and unmute yourself and ask a question.
Yes, thanks, Kaya. And thank you very much for this very informative talk. I have a question about the presentation of distributional data in the form of KDE plots. And I wonder how much or the kernel bandwidth really matters, or like I wonder about the importance of the choice of fixed bandwidth. And in that sense, also whether there is any good guideline to make my interpretation visually transparent through this bandwidth. And also, in which cases do adaptive bandwidth make more sense rather than choosing fixed ones?
Great questions. Let me see. Yeah, bandwidth. I really should have let me see if I've got. I should have. Give me a second. Ah, okay. I had a presentation on bandwidth. Oh yeah, there we go. Let me just, it's a different presentation that I gave in Germany a while ago. So let me just share my screen again. All right, slideshow. Okay, bandwidth, for those who are not familiar with it, is a similar concept to binwidth. So before PDPs were a thing, people in the very early days of detrital geochronology used histograms. So you're all familiar with histograms, bar charts. There are two problems with histograms. First of all, you need to decide where to put your bins. If you shift them a little bit to the left or to the right, you get a different looking histogram. And second, how wide your bins should be. And over the years, many different rules of thumb have been developed. Sturgis rule, Excel just uses the square root of the number of values. There's more sophisticated ones. None of them really work in all cases. Now, if you probability density plots got rid of that problem by just using the analytical uncertainty as essentially the bandwidth, which is the width of these different kernels here. It just took them from the analytical uncertainty. But as I said, that causes problems, which are solved by kernel density estimation. But then kernel density estimation still has this standard deviation of the kernels to be decided. And in my presentation today, I didn't have time to go into the details of this. But it's an area of active research. There's a Wikipedia page on kernel density estimation that has links to lots of guidelines for how to choose your bandwidth. I might want to add that there's no Wikipedia page on probability density plots, confirming that this is something that was just invented by geologists. Doesn't make real geological sense. So bandwidths, like histogram bin widths, have been studied in many by many different people. If you have a unimodal distribution, there is something equivalent to Sturge's rule called Silverman's rule. Of course, most of the data sets that we work with as geologists are not unimodal, they are multimodal, and then Silverman's rule will tend to oversmooth your distribution. And that's where adaptive kernel density estimation is another whole range of bandwidth estimators in which the bandwidth is allowed to vary. It's a bit similar to probability density plots, but of course the width of the kernels is not related to the analytical precision, but simply to the space between the samples. So in areas where you've got a lot of measurements, you can afford to use a smaller bandwidth. In areas where the data are spread out, you use a wider bandwidth. So these are called adaptive kernel density estimation methods. I don't have a slide that shows the default way that was introduced in Density Plotter. Comes from a paper. I can find it for you. Okay. It's Botev kernel density estimation. There we go. So this is a paper with 1,862 citations. It's very popular. It's also in the Wikipedia page. It introduces an algorithm that I find to work very well with multimodal distribution. So that's the default value that is used in provenance in my density plotter program and in isoplotter, but it won't always work. And in the case of, for example, the tritozircons applied to multiple samples, the bandwidth will be a complex function of the distribution of let me just turn this, of the number of grains. The larger the number of grains, the narrower you can afford your bandwidth to be. And so if you've got multiple samples, then if you don't use the same bandwidth for all your samples, then some differences here between this sample and that sample here, for example, could simply reflect the fact that the bandwidth is narrower. So a bandwidth, I think that's where, yeah, there's no one algorithm. Botev algorithm is a good start, but kernel density estimates are a visualization technique. And just like a histogram bin width, there is no perfect answer. And you should not feel afraid to change your bandwidth. Make it a little bit narrower, a little bit wider in order to make your plot look more useful. As long as you don't exaggerate. If you make your bandwidth very narrow, for example, kernel bandwidth, if I change it to 5 million years, then yes, you can, it turns into a PDP essentially. That's not very useful. So I would recommend that you use the Botev algorithm as a default value, and then you can change it a little bit as long as in the figure caption of your paper you explain that I've used this bandwidth. That's fine. It's just like a histogram. When you have a histogram, you want to demonstrate or you want to report your histogram bandwidth, and you want to do bin width. Sorry, you want to do the same with the bandwidth. So I know this is so another thing I do is I normalize the areas under the KDEs. If you don't do that, so again, some of these plots are going to be lower than others. Oh, sorry, here they're all the same. It doesn't really show the size of the peaks. The volume of the peaks is different. So there are a few tricks here that can be used to make your plot look more geologically interpretable, to make the differences in bandwidths not distracting. Don't know if that answers your question.
Yes, thank you. May I just ask about the adaptive bandwidth?
Yeah.
Does adaptive bandwidth at all make sense when I do these comparisons as such, or is it better to rather use fixed bandwidth in order to be able to compare better?
Yeah, so I think in isoplotter and provenance, adaptive bandwidths have been turned on by default. The adaptive algorithm that I use is a very simple one. It doesn't make a huge difference to your plots, but it makes the tall peaks a little bit sharper because you've got higher resolution there. Yeah, I think it's a good thing. It does have a theoretical foundation, and it will just make the best use of the information content of your data. You've got a lot more information in these areas with a lot of, let me see, KDE. So it will give you more resolution in the areas with a lot of data, and it will spread out the lower peaks. Let me just see the difference between, let me just explore, what's going on? Isoplotter, let's have a look. Others, KDE, options. So I'm going to turn adaptive off. Let's see. So it makes your plot a bit sharper, right? Which is not a bad thing. It's not going to shift any of your peaks. Again, it's just a visualization tool, mostly. But it's a visualization tool that, in the limit of infinite sample size, does converge to the true distribution of your data, which is not the case for probability density plots. And both adaptive kernel density estimation and ordinary kernel density estimation will converge to the true distribution at infinite sample size.
Okay, thank you very much.
Thank you, Kara. Hansi, you have as well a hand up, so if you would like to come in and unmute yourself and ask a question.
Yeah, thank you, Kara. Thank you, Peter. Really nice talk. And I also do some work in the provenance of the Loess. I think we met both of you at conference or something. Yeah. So really nice talk. Thank you, Peter, for this talk and also the efforts to analyze the provenance data. So we also have, I totally agree with you that we need to use big data, both on the size of the analysis and on the method. We will give talks on the provenance of Loess in the Loess Fest, and I will present the Detrital zircon. We have tested 4,400 ages of the Chinese Loess, and also some of our students have tried the heavy mineral and assemblage analysis using the SEM. So it can give you the estimate of the mineral assemblage not only on the heavy ones but also on the light ones, which can also give you some information. So just some questions. The first one, the MDS is really powerful tools we have to admit, but it's in some case the statistic method. So, for example, if I have two peaks, two provenance peaks, one I have 200 million years of the Detrital zircon peak, and the other has 250 million years peak. In some way, it may, in some cases in the MDS, it will, put them. It will give some similarities to the two samples because the two peaks are close to each other, but actually this is two different geological events. So have you thought about to put this kind of thought in the MDS analysis so that, yeah, that's my first question. Yeah.
Yes. So indeed, this is a very timely question because it's something I'm working on at the moment with a colleague from Imperial College. So the Kolmogorov-Smirnov distance, I think we'll do the opposite of what you said. So if you've got one peak at 200 and one at 250, two like narrow peaks, it will as long if they don't overlap, the difference between them will be extreme. So if you've got two peaks, for example, one at 200 and one at 205 million years, it could be an analytical issue. NDS is going to, or the Kolmogorov-Smirnov distance is going to pull these samples apart, not for geological reasons, but because of analytical reasons. Anyway, there are other dissimilarity measures that we are exploring. Like the Wasserstein distance is one that I'm exploring with my colleague. That will hopefully address those kinds of issues and capture geologically meaningful differences between samples more effectively than the Kolmogorov-Smirnov distance. Another thing I would like to maybe pay or bring to your attention is the possibility to visualize uncertainty of multidimensional scaling configurations. That's a relatively recent addition to the provenance package, but it is now possible with bootstrapping to visualize the uncertainties of an MDS configuration. Maybe I'll, this is very dangerous, but maybe I'll try to give a short demo of the provenance package. So I have opened RStudio, which is the most popular way of interacting with R. I can load the provenance package by simply typing library provenance. I can also just tick a box over here. But there we go. And then if you want to use the query-based user interface, you just type provenance and then, yes? Sorry, I got some echo here. In any case, let me just have a look at help of NDS. So that shows a number of options. And I saw in the chat there was somebody who was asking how to do three-dimensional multidimensional scaling. Well, you can do that using this optional argument K, which is the number of dimensions of the solution. So if you've got a very big data set, sometimes 2 dimensions do not capture all the variability. If you want to have 3 dimensions, you can do that. But of course, multidimensional scaling, the key usefulness of the tool is the fact that you can reduce multiple dimensions to 2 dimensions. But if you've got 100 dimensions in your problem, reducing it to 3 dimensions is also a big improvement, right? So that option is there. And then we've got NB, which is the number of bootstrap samples, which could be used to constrain a confidence interval. Let me just very dangerously plot NDS namib $DZ. So this may look scary to you if you've never used R, but you can do the same thing from the query-based user interface. If I set NB equals to 10, it's going to calculate confidence regions for all this. It takes a bit longer because it has to do the multidimensional scaling analysis 10 times. There we go. So it tells me that the location of T8, N1, etc., they're all subjected to sampling uncertainties, right? So not all the differences that you see are really real. Some of them are just if you were to collect new samples from the same locations and date different zircons, you will get slightly different results. And this kind of polygon allows you to visualize the effect of that. It makes the plot look quite cluttered, but I think it is quite useful to kind of assess whether the difference between N11 and N12 really is significant or not. So 2 things. So there are ways to maybe, if you don't trust the pattern that is shown on the MDS plot, look at the shepherd plot, look at these polygons, and then in the future there will be alternatives to the Kolmogorov-Smirnov distance that I'm pretty sure will address some of the problems that arise in some data sets.
Fantastic, thank you. I'll ask two more questions and then we'll move to the presentation. So a question that was sent to me. I am an undergraduate student major in geoscience. Recently happened to read your paper, Tectonic Discrimination of Basalts with Classification Trees, published in 2005. I am actually doing some exploration in a similar domain at present. In your paper, the method of building trees is based on relatively rigorous mathematical way and obtain very good results. After so many years since the publication of your paper, with the development of computer science, I believe maybe some machine learning algorithm, which is not as rigorous as traditional method in mathematics, can make the trees or discrimination diagrams even more effective. So my question is, do the discrimination diagrams generated by machine learning methods have equal geological significance as the traditional one, or a geological aspect, especially provenance analysis aspect? How much value do those untraditional discrimination diagrams have? Were you able to follow that, or would you like me to send that to you as well?
No, that's that's I'm happy to answer that question. So yes, I have actually seen some papers have been published in the recent past where people use neural networks and random forests, for example. Random forests are a generalization of decision trees, actually invented by Leo Breiman, the same guy who invented decision trees, came up with random forests, and they outperform decision trees. So they work better, but the problem is that none of them really are interpretable. They just, you give your data to an algorithm and it spits out an answer, and you can't really see how that answer has been arrived at. So maybe I can also just advertise a little program that I'm also working on. It's called GeoPlotter, and it's going to do lots of geological plots, including these trees. So this is these decision trees. I've got all my trace element compositions here, and let me see if it works. There we go. So that's a decision tree. It's very easy to interpret, right? If yeah, you can just by eye, you can see why it has decided that your ophiolite is an island arc basalt. So that's the advantage of these old-fashioned trees. The disadvantage is that they're not quite, they are outperformed by random forests. So I think there's still a place for these. Maybe I don't know.
Thank you. So the last question of the session, because we're running out of time, we could talk probably all day if we were allowed the space. I think quite an important question. I concern about multiple cycles of some minerals such as zircons, which may have some influence on the results of your data. How can we identify the multiple or fast cycles of minerals?
Yeah, again, it's something that I'm working on. So I was involved in a study where we use Raman spectroscopy. The paper is by Alberto Resentini. I'll find it for you. Okay. Is it with one or two S's? No, pretty sure. Vermeesch. Raman. There we go. So we can use Raman spectroscopy, which is a technique that can measure the radiation damage of samples. Anyway, I'll let you read this paper at your own leisure. So recycled zircons, for example, you've got a 1 billion-year-old zircon that is caught up in a mountain building event. If the zircons have been heated to more than a few hundred degrees, any alpha radiation damage that has accumulated in the crystal lattice will be partially or completely reset. And we can measure that very easily using Raman spectroscopy. So Raman spectroscopy is a technique whereby you shoot a laser, non-destructive laser, at a sample. It interacts with the crystal lattice and it returns photons with a characteristic shift that can tell you what the mineral is. In the case of zircon, the more damaged the zircon is, the more damaged the crystal lattice is, the broader the peaks of the Raman spectrum will be. So this is one way in which you can see the difference between a zircon that has never been reheated and zircons that have been reheated. Similar, but older approach has been to use zircon fission track dating and zircon helium dating. If you double date grains, uranium, lead plus helium, or fission tracks, again, you can see the difference between a recycled zircon potentially and a non-recycled zircon. But the problem with helium and zircon fission tracks is that they're very time consuming. Raman should be a lot quicker, but this is active research. We're working on that. Hopefully within the next few years, more progress will be made in that front. And I think that's a very promising way to address this big issue of recycling, because I found it in many places, like in the Sahara. We had this study, also showed up on the Google Scholar results. We measured sands from Morocco to Arabia, and the uranium lead H spectra were all the same, because it's all recycled sands from the Nubian sandstone. We hope that by analyzing other things in the zircon, we might be able to pull apart these zircons. But in the meantime, thermochronology and other provenance proxies, I think, are the way to go. If you combine heavy minerals with zircon, uranium, lead geochronology, you're always going to get more information out of your data than by just relying on the zircons.
Fantastic, thank you. So sadly, we just don't have time to address all the questions, but I'm sure if you drop Pieter an email, he may be able to help.
Yes,
And
yes.
so Singbal Gao had prepared a presentation. So if you are still keen on presenting your data, I'll invite you to share your screen now.
Okay. Thanks, Kaya, and thanks, Peter's excellent presentation. And here I want to share some of my new results. Can you see my screen? Okay.
Yes.
Good morning and good afternoon, every colleagues. My name is Xinbo Gao from Institute of Geology and Geophysics, Chinese Academy of Sciences. And actually, I didn't do any provenance studies, and I mainly focused on the magnetic properties of Loess deposits and their paleoclimate implications. And here I just want to share some of my personal ideas about the provenance studies of Loess deposits, and some new results of the pale wind direction determinations of the Loess deposits from the Chinese Loess Plateau. And indeed, the geochemical evidence is very important during the provenance studies of the Loess deposits. And in the last 5 to 10 years, many beautiful papers about the provenance of Loess deposits have been published, mainly based on the geochemical evidence. But what I want to say is that during we interpretation this geochemical evidence, it's very important to considering the general atmospheric circulations of the proven directions, especially for the alien deposits, because for the Loess deposition, the CO2 materials in the dust source areas have been transported by long distance by the alien dust bearing wind to the deposition areas. And if we just rely on the geochemical evidence, it may reach to some misleading conclusions, and the pale wind directions can help a lot in the interpretation of the provenance discriminations, because it's easy to understand that the dust source areas it should be and must be located in the upwind directions of the deposition areas. And the anisotropy of magnetic susceptibility provide us a very useful approach to determine the tailwind directions. And I believe for many Loess researchers, we have the experience when we measuring the magnetic susceptibility in the different sample orientations, we will get different values, and it's called the anisotropy of magnetic susceptibility. And during the deposition of these magnetic particles, the orientation of these magnetic manuals is parallel with prevailing dust-bearing wind. And if we measure the anisotropy of magnetic susceptibility, we can know the pale wind directions. And next, I want to share some of my new results about the pale wind directions and its implications for the dust provenance. Traditionally, the dust source areas of the Chinese Loess Plateau are the large arid areas in the northwestern China, including the deserts and the Gobi Desert. And however, recently, some researchers proposed that the Kaidan Basin is also a very important dust source areas, mainly based on the geochemical evidence. And we think the pale wind directions can help to solve these problems because the western Loess Plateau is located closer to the Kaidan Basin. And if we can determine the pale wind directions is pointed to the west, that means the Kaidan Basin is an important dust source areas. If not, the winter monsoon and the must be the dust source, dust bearing wind, and the desert and the Gobi Desert will be the important dust source areas. And in the northwestern Chinese Loess Plateau, we collected two parallel sections covering the last interglacial and glacial times. And here we show the depth variation of the magnetic susceptibility of the two sections and their comparison with the Bennett's oxygen isotope records. And in the right hand, we show the AMS results, the pale wind direction results. And it's clear that for the for both the two sections, the interglacial and glacial periods all shows dominant pale wind directions pointed to the northwest. And instead of the westerlies, that means that the northwest winter monsoon is a dominant dust-bearing wind, not instead of the westerlies. And our results is consistent with other AMS evidence from the other sections on the Chinese Loess Plateau and the sedimentary evidence, mainly the spatial variation of grain size and the thickness of the Loess deposits. And based on this evidence, we excluded the contribution of the Kaidan Basin to the dust of the Chinese Loess Plateau, and move to our my conclusions. And I think it's important to keep in mind that besides the geochemical evidence, we must consider the atmospheric circulations and the pale wind directions during interpretation of the geochemical evidence of the Loess deposits, and we will make better provenance interpretations. And that's all my sharing. Thanks.
Thank you very much. Are there any questions or any comments that anybody would like to add to your presentation, or have you got any specific questions for Pieter?
I had a question about this presentation, actually. So I thought that magnetic minerals align themselves along the Earth's magnetic fields. So you say that it's the wind. What happens when the magnetic field flips from north to south?
Yes. For the magnetic, for the alignment of the magnetic properties, the larger here, because this is the Loess deposits and the dust, the dust is from the arid areas, and the magnetic minerals always is very coarse, is coarse grain size, and this coarse grain size usually magnetite. Magnetite, their element is their element can orientated parallel with dust bearing wind, and for the from the finer grain size is always re-element, always easily re-element with the magnetic field, and in the western part of the Chinese Loess Plateau, it's very close to the dust source areas, and the magnetic minerals is very it's coarser, and these minerals can record the tailwind directions.
Okay, thank you.
Thanks for your question.
Thank you very much. I think we're going to draw the session to the close then. I would like everybody to join me in thanking Pieter for joining us and giving this excellent talk and overview of statistical methods and approaches to provenance. So silently or actually join in. Thank you very much, Pieter. And before we all log off, just a quick reminder that this is the second session of the week. And tomorrow we have Gabor Ruvari joining us and talking about the paleoclimate proxies indicators in Loess. On Thursday, we have Samuel Olvani talking about dust modeling. And on Friday, the final talk will be covering the quantitative paleoclimatic reconstructions in Chinese Loess by Lu Yu. So thank you very much, everyone, again, for joining us. It was a wonderful session. We had an excellent turnout today. And thank you again, Pieter.
Thank you, Pieter. Thank you. Bye-bye.
My pleasure.
Thank you.
Bye.
Thank you, brother. Good luck with the rest of the week.